Chapter 3 on series. First of all, let's go through the notation. Sigma notation is simply represents sum. So rather than saying Sn, which would be the sum of n terms, what you could write is sigma, which is a Greek letter, S for sum. There will be n terms, so you put n here, but you're going to start from the first term. So this is the first term all the way up to n terms. However, we've got to write down the rule for the nth term. So here you will have the, I'll call it rth term, and you will see why. Because we've got to put r equals 1 because it's our dummy variable, and we're going to just write a general ur. So that would be u1. So whatever I get, if I substitute 1 into that, add u2, add u3, add all the terms up to un. So this is what sigma notation means. Sometimes we use r, this dummy variable. It only acts like to signify the position of each term here. You could use I or k, but in the book, in the course that you're doing, most of the time they will use r, but not solely. You could have an exam question with a different dummy variable. So here, for example, we've got a sum. It's clearly the sum of natural numbers, your counting numbers. So how could I write it down? It's really important to get used to it. So you could write down that there is 1, 2, 3, 4, 5, 6, 7 terms. So it's the sum of 7. So you have all the way up to 7, but you will start from r equal to 1. And then when r was equal to 1, you had 1. When r was equal to 2, so the second term, it was 2. When r is equal to 3, then it was 3. So really the rule here for the rth term is r. Whatever the position we're talking about, this is our number. Okay, so over here we've got a very similar situation, but there's only 1, 2, 3, 4 terms. But we are going to begin from 7. So you could rewrite it as r equals to 7 all the way up to 10. And the rule is r as well, the r term. Okay, here we've got 1, 2, 3, 4, 5. So we are going to have 5 terms. The first term is 5. The second term is 5. The third term is 5 all the way to the end. So it doesn't matter what r is, you're always going to be summing 5. So here 5 is going to be written 5 times. Now here it's very similar, but we've got 1. That 1 is written 4 times. And there is 1, 2, 3, 4 terms. Now for this one, for the next one, I want to actually work out what it is. So the sum of the terms from 1 to 4 of 1 is simply, how many ones have we got? 4. 4 times 1, so it's going to be 4. Now what happens if I've got n lots of 1s? Well, I'm going to have how many terms? N, so it goes from 1 to n, and I'm adding 1 all the way through. So how many 1s have I written down here? N lots. So it's n times 1, which is n. And this is a very, very important result that you will be using throughout the book. So if I have this, that can be replaced with n. Let me just go through this one. If I have this, that tells me that I've got 5 lots of 5 because it's been written 5 times. So it's 25 for constant term. Okay, what about this one? So you can see that these are square numbers from starting from 3 squared, then 4 squared, 5 squared, all the way up to n squared. So definitely finish on n, but the starting position is 3. And then you've got 3 squared, and there's somewhere there's r squared. So there you go. Okay, so we're going to just to show you what I mentioned, sometimes you could have I, so you could have I equals to 1 up to 5, and the rule could be 2I plus 3. And then you work it out by putting 1 into this, so it's 2 times 1 plus 3 as your first term. Then you put 2 into this, so it's 2 times 2 plus 3. Then you put 3 in, so it's 2 times 3 plus 3, and all the way up to 2 times 5 plus 3. Okay, we could work out those terms. So that's how you could use it with a different letter. Okay, so let's have a go at example 1. We are asked to evaluate, so find the answer to the sum of those terms. So it's actually similar to the example I've just given you. Okay, so let's work out, if it's only 1 to 4, it's really quick job to work out all those terms. But there is, for anything like from 1 to 50 or bigger amounts, what you want to do is have a formula, the general formula for that situation. So actually, before I do that example, let's just show you what would be the sum of what's called natural numbers. So it's the sum of r. So when r is equal to 1, it's going to be 1. When r is equal to 2, you're going to add 2, 3, all the way up to n. Now there is a formula which you need to know, which you need to learn. I want to derive it with you. So I'm going to write my sum using Sn. So this is what we need to work out. Let's put the last but one term and the last one as well. Okay, now you're going to rewrite the same sum again, but starting from the end. So you have n, then you will have n minus 1, then you would have n minus 2, all the way, and I'll write underneath this the first term, and then underneath this one too. I'm not going to bother with 3. So what I've done, I wrote my series from 1 to n, and then wrote it backwards from n to 1. Now the way to work out what the sum of n terms is just working out what Sn plus 2n gives you. So 2 lots of Sn. Let's have a look. So what do I get? I will have 1 plus n. So I'm matching up the pairs. Okay, so the first term with last, that gives me 1 plus n, or n plus 1. And I will match the next pair, so we'll have 2 plus n minus 1. Well, that also gives me n plus 1. Now I wrote the next one, so let's see what I get for this one. I will have 3 plus n minus 2. That also gives me n plus 1. And then if I go to the last term and the one before, I will have n minus 1 plus 2, so n plus 1. And the last pair here is also n plus 1. So matching those pairs and matching all the pairs between 1 and n will generate n lots of n plus 1. So you've got 2 Sn. Now how do I write it? Well, multiplication. but obviously we wanted to know what Sn is, which is a half of n plus 1. So the formula you need to remember is the sum of r is a half of n times n plus 1, and the sum of 1 is going to be equal to n. There you go. These are very important results, and we're going to just use them in the example 1. So starting with the first example, so I was saying if it's only 4 terms, you could actually work them out very easily. So do 2 times 1 minus 1, so that would be 1. 2 times 2 for the second term minus 1, so that gives me 3. And then you've got 2 times 3 minus 1, so it's 5. And 2 times 4 minus, that gives me 7. If I add them, you're going to get 16. So let's see if we can actually work out this answer in a different way. So we know it's going to be 16 because I've just worked out each individual term. But let's have a look if we can work it out in a different way. So here is the rule. If I'm summing 4 lots of 2r, this is the same as 2 lots of the sum of r. Now we'll mention that result in a minute in the next example. And then minus 4 lots of 1s. Let me show you why this is so. Okay, so when I do work these out, I did them quickly in my head, but let's do it slowly. So we'll have 2 times 1 minus 1. Then I have 2 times 2 minus 1. Then it's 2 times 3 minus 1. And lastly, 2 times 4 minus 1. So why would that be the same as 2 lots of the sum of r? Well, if you just look at these at the start of each bracket, so you can see clearly that this generates 2 times 1 plus 2 plus 3 plus 4. So 2 lots of the sum of r from the first to the fourth. And then you've got minus 1, minus 1, minus 1, minus 1. So you've got minus 1 plus 1 plus 1 plus 1. So here is the proof that you've got 2 lots of sum of r and minus this sum of 4 lots of 1s. Let's see whether the formula that I've given you will give me the same answer. So this formula you need to learn, and the question in the exam, it will ask you to use standard results to show something or calculate something. Okay, so 2 lots of our formula. Now I'll keep it with n, but I'll replace it with 4 in a minute. Minus, remember the formula for this one is simply n. So this one is going to be minus n. But our n is equal to 4. That's the number on the top of each sigma. So this one here is going to be 4 times, so 2's cancelled, and you've got 4 times 5 minus 4, which is 16. Okay, part B, we are going to find the sum of 50r. So the formula is written. I always copy the formula, write it down in the exam, and then we're just going to put n is equal to 50, and you come up with a half times 50 times 51. So that's going to be 0.5 times 50 times 51. That's 1275 And finally here we've got to add all the numbers from 21 all the way up to 50. So the way to do this sum is simply realize that you want to find the sum of all 50 terms from 1 up to 50 and subtract the terms that came before 21, because we're only interested in 21, so be getting rid of the first 20 terms. Okay, so S50 we've already found out, that was 1275, and this one is going to be a half times n, which is 20, and times 21, so that should be 210. So it's going to be 1065. Good. Let's have a look at example 2. Now, before we do the example 2, let's just generalize this result. So if your starting point here, if you have to, in general, find the sum of some R formula f of r between k and n, then you always need to imagine finding all the terms from 1 to n, following whichever rth room is, but you also have to get rid of, because you want to keep k and you don't want to keep anything that came before k, so we must take away k minus 1 from 1 f of r. So it's like if you had to write your terms in the long way. There you go. You carry on. Then you want to take all of them, which is your Sn, and you want to subtract Sk minus 1. There you go. Let's move on to example 2. So this time we're going to show that this sigma gives you that result for n greater or equal to 3. So here we're going to apply the rule that this one, it's like having the sum of 2n minus 1. That starts from 1, so we want to get rid of initial 4 terms, so minus s4. Okay, so it's going to be, first of all, let's just copy down the result that we're going to use. So this is r is equal to a half n times n plus 1. So we've got a half times our first n is capital 2n minus 1. And then you've got 2n minus 1 plus 1 minus a half of, we've got our n is 4 times 4 plus 1, which is 5. So this one will go to 10. This one here, you are going to have to just tidy this bracket up. So the 2.5 cancelled. So we've got 2n times n, so it's 2n squared minus n minus 10 as asked. Okay, so let's have a look in general. This is something I've already mentioned. So if you have got a number in front of your function, so for example, if you did sigma 2r, then you could just work out 2 lots of sigma of r. So rather than thinking about 2 times 1, 2 times 2, you could just work out what the sum of r is and then multiply the result by 2. If you're adding them, it's exactly, we've done this, so when you add it together, you could just find the separate sums and then add the 2 results together. So it's quite intuitive, I think. Normally that's what people do. Okay, so let's moving on to example 3. So using the results from the previous part, we are going to think of it as 3 lots of the sum of r from 1 to 25 plus the sum of ones. Okay, so 25 terms. So this one here, our n is going to be 25. I said always quote it. This is not in the formula booklet, so you need to memorize it. So it's a half of n times n plus 1. So it's 3 times a half times n, which is 25, times 25 plus 1, which is 26. Plus this one here, you've got 1 plus 1 plus 1, 25 times, it's 25 times 1, which is 25. Okay, so let's just pop these values into the calculator. You've got to do 3 times 25 times 13, which is 975 plus 25. That is this beautiful number, 1000. Example 4. Show that the sum of n terms from 7 with the nth term rule 7r minus 4 is equal to this expression. So you're going to start from the left hand side, and I'm going to split it straight away into 7 lots of the sigma from r equals 1 to n r minus, now I like to write this one as 4, the sum of n lots of 4, rather than, so you might choose to do it as 4 lots of n lots of 1s. For me, this means 4 at 4 at 4 n times, so I've got 4n. It's up to you. So we're going to use the formula 7 times a half of n times n plus 1. So this is the formula, and minus 4n. So what we need to make it look like this, so it's going to be 7 over 2 n squared plus 7 over 2n minus 4n. So 7 over 2 n squared minus 1 half n. So 7 n minus 1 over 2 times n, which is, okay, they've put n in front, so let's just write it down. Okay, so proven. Now hence show that the sum of these two, no, it says hence evaluate. Okay, so in this case, you're using the results from the previous part, which is a half of n times 7n minus 1, and you put 50 in, because you're going to find the sum of 50 terms, and that would start from 1. So you need to subtract all the terms you don't want to. So you don't want the first initial 19. So we're going to put 50 into the first one, so it's 50, and that would be the sum of all the terms from the first to the 50th. And then we're going to get rid of the initial 19. So it's 7 times 19 minus 1. So pop it into the calculator. So it's 0.5 times 50 times 7 times 50 minus 1 minus 0.5 times 19. No, actually what I'll do, I will split it, but you can just do it all in one go at this stage because I've already shown the substitution. So the second one is going to be 0.5 times 19 times 7 times 19 minus 1. So it's 8725, subtract the last answer. That gives me 7471. Okay, so you can move on to exercise 3A and practice questions in there.